Welcome everyone in the Crystal Clear Electronics 2, Chapter 20. In the next video parts, we will take a closer look on power requirements of microcontrollers for different clock frequencies and operating modes. Our lead presenter in this chapter is Előd Kovács, who you might have seen in previous chapters.
I also welcome everyone. It is true that I have appeared in previous videos before, unlike my colleague Balázs Böröczky, for whom this is the first time. If I know correctly, you're part of the BME Formula student team. Can you tell us a little bit more about that?
Yes, I am indeed a member of the BME Formula Racing team, who are developing an electric race car. My main focus is the development of embedded software for low-voltage control electronics. The topic of today's chapter is very much related to this task, since my team also encountered very similar problems, such as the extra heat generated by overheating due to the high power consumption of microcontrollers, but this is just one example among many.
As Balázs has already mentioned before, in this chapter, we will look at important techniques, tips, and tricks for energy management in microcontrollers and embedded systems more generally. There are many tasks, whether as a hobby, project work, or workplace development project, where it is necessary to find a balance between computing power and energy consumption.
Finding this balance is by no means a simple task, with many different factors to be considered in combination for a given application. For example, the microcontroller that runs the vehicle dynamics software of our car manufactured in our workshop has to perform very heavy computational tasks in real time. In its case, it is particularly difficult to find a mode of operation where it can still handle this computational demand without overloading itself in terms of power consumption.
In general, the best answer to the questions raised in this chapter is, it depends. For each task, we need to consider the priorities of the application in terms of minimal consumption and computational performance.
Let's not waste any more energy, it's time to start our current topic. The chapter was written by László Iványi and proofread by Ádám Szabó.
The current requirement of a given microcontroller depends on its clock frequency, which is given in microampere over megahertz in the datasheet and in related articles. If we rely on this information only, we can influence the consumption by the current consumption or the clock rate.
For example, if we want to develop a watch, it can be done only after careful consideration. We brought this simple clock, which currently runs off a power cable, but smaller clocks like this can be powered up to 10 years on a single coin cell, but in return you get a simple 7-segment LCD display where you can at most display the date and the time.
At the other extreme are the very popular smartwatches. Here, similar to the other example, uptime is important, but it is a lower priority because of the much higher computing power requirements compared to the previous case. In this application, we need to be able to run, for example, a fully fledged Android operating system with a touchscreen, a complex menu system, and many extra peripherals. Their use has a big impact on battery life, so as you may already experienced, smartwatches sometimes need to be recharged every 2 days, while simpler watches can last for years without charging batteries. Of course, there is still a place for both solutions, just in different market areas. In our later tasks also, the specific goal will determine what becomes a priority and where we place our device on the scale of low power and computing performance.
And now, let's dig deeper in our topic, starting with different modes of microcontrollers. Let's see what kind of built-in power management capabilities does our STM32F446 microcontroller have.
Low power modes are available, which are basically needed because the controller's power consumption in normal run mode remains in the area of milliampere even when there is no task execution, only initialization of all necessary peripherals. Thus, when the processor is not needed to run, for example because the system is waiting for an event, we can set different power consuming states. We will discuss these now. The first is the normal mode, also known as run. When using the run mode, the controller runs without any limitations after initialization based on the clock, pin, and peripheral settings we have specified. This is the default operation. After power is applied, the device will boot in this mode even if a bootloader starts our application. In this mode, we can reduce power consumption by setting a lower frequency clock for the microcontroller. In this mode, the microcontroller is also able to detect any configured interrupt or use any initialized peripheral. The next bigger group contains the low consumption modes. The low power modes handle the power supply to the components in the controller in different ways. Linear voltage regulators, which are LDOs, short for low dropout regulators, can be found inside the case. These supply all digital circuits except those on the backup range line. For different modes of operation, we can switch off the peripherals from this 1.2 volt power line.
In the upcoming minutes, we will show you a table that summarizes the low power modes, except the VBAT. We will review the wake-up options for each mode, and the effect on the 1.2 volt supply, the controller's HSI and HSE clock sources, and the internal voltage stabilizers.
One low consumption mode is the sleep mode. Using the sleep mode only shuts down the processor, clock, but the peripherals continue to run at the preset clock frequency. This way, they remain fully functional and are able to generate interrupts. From this state, any configured interrupt will cause the system to enter normal mode, which will occur almost immediately. The next mode is the stop mode, which has the lowest power consumption while retaining the contents of the registers and the SRAM, which means static random access memory. However, it also disables the PLL, phase locked loop, HSI, high-speed internal clock, and HSE, high-speed external clock sources, as well as the clock of all components on the 1.2 volt network. To return from stop mode, an internal or external interrupt associated with an EXTI, which stands for external interrupt, channel of the microcontroller must be asserted. Next in line is the standby mode, that is the lowest power state in which there are still interrupts that, if their condition is met, in other words fire, can put the controller into normal mode. Such interrupts are a rising edge on the wake-up pin or the following RTC events if previously set. These are, for example, RTC alarm, alarm A or alarm B. These are preset to alarm in a given time. RTC wake-up event, RTC tamper events, RTC timestamp event, NRST pin for external reset, IWDG, which is an independent watchdog reset. The 1.2 volt internal power line is disabled as the internal voltage regulator is also disabled. The SRAM and register values are lost in this mode, except for the backup registers, which are the RTC registers, the RTC backup registers, and the backup SRAM registers. The consumption of this mode even depends on whether the SRAM backup and RTC registers are enabled. The transition from standby mode back to run mode has a duration of 375 microseconds.
In addition to these, we have a VBAT mode, where the internal power supply of the microcontroller is switched off, thus requiring an external power source which can supply power to the peripherals on the backup power line, which are the RTC registers, the RTC backup registers, and the backup SRAM.
With this mode, even after a power failure, the time settings and the data saved in the backup SRAM will be preserved. It's also good to know that the only way to wake the microcontroller from this mode is to restore power to it.
And now, let's talk about energy-saving techniques of both software and hardware approaches. Let's first see how to set up the earlier discussed modes from software. To do this, open the example project for the chapter, open the main.c file, and find the handle state function. In this, you will see a switch structure, where each case handles the different modes.
When setting the sleep mode, we first disable the interrupt generated by the SysTick timer peripheral so that it cannot wake up the microcontroller. Then, we call the hal_power_enter sleep mode function, which has two parameters. The first, to switch the internal power supply to low power mode, and the second, to specify the external signal to wake up the microcontroller. In this case, we want to wake it up for interrupt. In the parameter, we use the abbreviation WFI, meaning wait for interrupt. Finally, after waking up, we enable the SysTick interrupt again. In case of the stop mode, similar to the previous, we first suspend the SysTick interrupt with the hal_suspend tick function, and then enter stop mode by calling the hal_power_enter stop mode. In stop mode, the registers are cleared, so we need to reinitialize the clock settings after waking up. Finally, we enable the SysTick interrupt again. The implementation of the standby mode is different from the previous ones. Here we implement a wake-up timer. We first clear the flags associated with the wake-up to ensure a clean wake-up state. Then, we set a timer to wake up the microcontroller after 5 seconds. This has a time base and a count value, after which the wake-up occurs. The time base can be calculated from the division of the RTC clock signal, in this case the LSI clock signal. We've set a division of 16, so the time base is now 0.5 milliseconds. From this, we can calculate that the 5-second timer has a counter value of 10,000. If the setting is successful, the controller enters standby mode by calling the hal_power_enter standby mode function.
It's a good idea to use power modes dynamically, so that you always send the device to the lowest power mode that meets the requirements of the workflow.
This way, we can maximize energy savings. If we follow this principle and look at a slightly larger time slice, the average of the different mode consumptions can be calculated like this. I average is equal to I run times T run plus I standby times T standby plus I stop times T stop plus I VBET times T VBET. Then everything is divided by the total operating time. In this formula, I run is the power consumption in run mode, T run uptime, the amount of time the controller spends in run mode, I standby is the power consumption in standby mode, T standby uptime is the amount of time the controller spends in standby mode, I stop, the power consumption in stop mode, T stop uptime, the duration of the stop mode, I VBET, current consumption in VBET mode, T VBET uptime, the amount of time the controller spends in VBET mode, and T full uptime is self-evidently the total time our application has been running, which is the sum of the runtimes of all modes. Based on this, the average power consumption of the microcontroller can be calculated as follows. P average equals to I average times U supply voltage. Here the U supply voltage is the microcontroller's supply voltage, and I average is the previously calculated average power consumption of the microcontroller. This gives the average power and current requirements of the microcontroller. This gives a much more accurate approximation of how long the microcontroller can run on from a button cell or an 18650 lithium-ion cell, of course only after proper voltage level adjustment. For example, in very low power systems, it's worth including the self-discharge of the power supply in the power consumption.
I think this much information is enough for one video part. This first video was only the beginning. Stay tuned for the next video, where we will learn even more interesting things about energy saving techniques. See you there. Bye.
Bye-bye.